From the earliest civilizations to modern stargazers, the twinkling of stars has captured the imagination of humans across the ages. This mesmerizing flicker, though a simple sight, opens the door to a profound celestial ballet that has intrigued astronomers and poets alike. Imagine a star's light journeying across the vast emptiness of space, steady and unblinking. Yet as this light enters the Earth's atmosphere, it embarks on a turbulent path. The atmosphere, a layer of gases varying in density and temperature, bends and scatters the light, creating the twinkling effect we see. This phenomenon, while beautiful, is not just a treat for the eyes, but a puzzle for the mind. What can the dance of starlight tell us about our atmosphere and the universe beyond? How has this sparkling display influenced science and art throughout history? Let's unravel the mystery behind this sparkling celestial dance. To understand why stars twinkle, we first need to know a bit about light. Imagine light as a traveler, embarking on an epic journey from distant stars to our eyes. Light travels in waves, similar to how ripples spread across a pond when a stone is tossed into it. When light from a star races through the vacuum of space, it moves freely without interference. Space is a perfect void with no air or particles, allowing light to travel at its fastest speed, about 186,000 miles per second. But the journey of light doesn't end there. As it reaches Earth, it encounters the atmosphere, our planet's protective blanket made up of layers of gases. Here's where things get interesting. Imagine throwing a pebble into a still pond. The ripples travel smoothly. But if the pond were full of floating leaves and twigs, the ripples' path would no longer be smooth. They'd twist, turn, and change speed as they encounter obstacles. This analogy helps us understand the fate of starlight when it hits our atmosphere. Particles and various atmospheric conditions act like those leaves and twigs on the pond, disturbing the light waves. Each minute change in the atmosphere can bend, slow down, or scatter the light, altering its straightforward path. Different colors or wavelengths of light bend at slightly different angles when they pass through mediums like air or water, a phenomenon known as refraction. This is why a prism can spread white light into a rainbow. Imagine our atmosphere as a swirling ocean of air. This vast, invisible blanket wraps around Earth, composed primarily of nitrogen and oxygen, along with traces of other gases like argon and carbon dioxide. But it's not just the composition that's fascinating, it's the structure, divided into several distinct layers. Let's dive into these layers, starting with the troposphere. This is where we live and breathe, extending up to about 7 to 12 miles above the Earth's surface. The troposphere is the most dynamic layer where weather changes occur and temperatures decrease with altitude. Above the troposphere lies the stratosphere, stretching up to about 31 miles above the Earth. Here, the air is thinner and drier, and unlike the troposphere, temperature increases with altitude due to the absorption of ultraviolet radiation by the ozone layer. Next, we reach the mesosphere, and above that, the thermosphere, where the air grows even thinner and temperatures can swing dramatically. The thermosphere can reach temperatures up to thousands of degrees Fahrenheit, particularly when the sun is active. Each of these layers is in constant motion, with varying densities and temperatures. As starlight enters our atmosphere, it begins a turbulent descent. This journey, though invisible to the naked eye, is a fascinating dance of physics involving light from distant stars and the ever-changing layers of our Earth's atmosphere. Let's dive into the scientific phenomenon known as scintillation to understand why stars twinkle. Imagine starlight as a steady stream of photons traveling through the cold, empty space. This journey is uninterrupted until these photons reach the outer edge of Earth's atmosphere. Here, they encounter a blend of gases, each layer with its own density and temperature. As light moves from the vacuum of space into the air, it slows down slightly due to a higher density of the atmospheric gases. This change in speed as light enters a different medium is known as refraction. However, the atmosphere is not a uniform layer. It's a dynamic mix of varying densities and temperatures, constantly stirred by weather patterns and thermal activities. Each pocket of air with a different temperature or density bends the light at a slightly different angle. This bending or refraction of light is not consistent because the atmospheric conditions are always in flux. As a result, the path of starlight becomes erratic, causing it to zigzag or scintillate as it travels towards us. This scintillation is what we perceive as twinkling. Each shift in the direction of light, although minuscule, affects the brightness and position of the starlight when it finally reaches our eyes. It's akin to watching a light through the ripples on the surface of a swimming pool. The water's movement causes the light to dance, shimmer, and change intensity, similar to how atmospheric turbulence makes stars twinkle. Moreover, different colors of light bend by different amounts due to their wavelengths. Blue light bends more than red light, which sometimes causes stars to change colors as they twinkle. This varying refraction of different wavelengths adds another layer of complexity to the scintillating effect. Do all celestial bodies twinkle the same way? A question that might linger as we gaze up at the night sky. It turns out not all that glitters in the sky is due to the same reasons. Take planets, for instance. Unlike stars, planets don't twinkle. Why is this? Planets are much closer to Earth and appear larger in our sky. This larger apparent size means that the effects of Earth's atmosphere on the light coming from these celestial bodies are much less pronounced. While stars, being distant suns, are merely points of light, even through powerful telescopes, planets present a more substantial image that atmospheric distortions can't easily affect. Moreover, the light from a planet is reflected sunlight rather than light generated by nuclear fusion, as is the case with stars. This reflection, combined with their proximity and size, makes planets appear as steady beams of light in our celestial canvas. Tonight, when you gaze up at the starlit sky, you'll see more than just light. You'll witness a cosmic ballet choreographed by nature itself. In our exploration today, we've unraveled the enchanting phenomenon of Twinkle, Twinkle, Little Star. It all begins with the nature of light, traveling vast distances across the universe only to dance in the ever-changing Earth's atmosphere. As this light passes through various layers of our atmosphere, each with different temperatures and densities, it bends and scatters, a process known as refraction. This leads us to the heart of the twinkling effect, scintillation. Tiny air pockets in the atmosphere act like a multitude of prisms, causing the light from the stars to flicker and shimmer, much like the sparkle of a diamond when turned under a light. Beyond just stars, we've also glimpsed at how other celestial bodies behave in our sky, adding depth to our nightly celestial show. I hope you enjoyed this stellar journey. If you did, please like, subscribe, and share this video. Until next time, keep looking up and keep wondering.